Welcome everyone to this uh, webinar on what's new in 14.3 uh, as regards math computation and Wolfram system modeler. My name is Devendra Kapadia and I lead the mathematical computation team at Wolfram. But I think this release is a very exciting one for us because there's just so much to talk about. So today's webinar has not one or two or three talks, but four short talks. And I think of today's webinar as being broadly broken in two parts. And you can see that in these two rows away, the first row is what I would call pure mathematics or symbolic computation, and second row is more applied mathematics or even physics or engineering, depending upon your viewpoint. So the first talk for today is going to be on a very simple theme: what happens to the world if A times B is not equal to B times A and all your middle school math crumbles. And to talk about that, we have Adam Strazbonsky with more than 3 decades experience at Wolfram. It takes someone like him to reinvent algebra in this so-called non-commutative setting. So if you don't know this big word from middle school mathematics, I'm sure your teacher taught it to you. Non-commutative just means that A times B is not equal to B times A. That happens for matrices, happens for all kinds of other structures. But to explore that in depth, we have Adam to take you through his usual rigorous style of doing things. And I should say one last thing, that it's not something we did for pure mathematical reasons. We ran into trouble when we tried to simplify matrix identities, and you'll see a bit of that in Adam's talk today. So it's a pretty big project inspired by our own needs, but hopefully of use to the rest of the world. The second talk for today is on a much more mundane topic, something everyone knows: matrices. And there we have another extremely experienced and popular member of our community, Daniel Iqbal, with, again, more than 3 decades experience. And what he has done is to at one level, to fill in the gaps in our matrix functionality. This thing you see over here is something called a Frobenius decomposition. Some people call it a rational canonical form. But the key point is to try and make sure that we have all the tools in the system that people might want us to have. And as Danny might tell you in the talk, why have we not done before? Well, sometimes we didn't have the time, and sometimes we just didn't know how. And we have cracked all those puzzles in this release. So I think it's a big release from the mathematical point of view. But we also have some other exciting stuff. We had this long-standing program for finite element method computation. And we're coming to the point where we'd like to be more real world in our applications, even more real world. And that's the theme of axisymmetric flows, which Martin Vejvoda will speak about. So that's a big term, but it's the kind of thing you've seen pipes. What you see over here is a cross-section of a pipe with water flowing in it. But the pipe may have a complicated geometry. It might be big. So you need partial differential equations, you need geometry. And to put that all together has been quite a task. But Martin, with his mentor, Oliver, who's also here with us, have done a great job. So this beautiful talk on fluid dynamics is our third talk for today, the first applied talk, in contrast to the first two. And some people talk about distributed modeling, by which they mean that when you do finite element method, you have a large geometry and you have partial differential equations, etc. But then at the other extreme, you have so-called lumped modeling, which is what system modeler does, where you have small components, and those components are now governed not by partial differential equations, but by ordinary differential equations. But then the components must be linked, so you have differential algebraic equations. This is a very mature area, and now we're getting into all kinds of things like system validation, etc. And to speak about that, we have another very popular member of our community, Ankit Naik, who has got a beautiful talk. I've seen all the talks, I should confess, and you should. I'm sure you'll enjoy it if you stay all the way until the end and listen to Ankit speak about the latest in system model. So we have 4 talks, lots to talk about. We will go through the talks one by one and make sure that we cover everything. There'll be some time at the end for us to come together and talk to you personally. But meanwhile, we'll use the chat and Q&A to get things across to you. So I think we have a very exciting I'd say hour and a half before us. We have the Wolfram staff, Jamie and Robson, who are always around to help out, if you need things. But I think I won't say more. I'll just hand you back so that we can start the first talk by Adam Strasbonsky on non-commutative algebra. Thank you.
Hello, my name is Adam Strzepoński, and today I will be talking about non-commutative algebra. So Mathematica 14.3 contains new functionality for computation with non-commutative polynomials, including polynomial transformations, polynomial reduction, and Grosvenor basis computation. In my talk, I will present the new functionality and show some examples. So first, let me show new non-commutative polynomial functions. So for algebra representation, we have non-commutative algebra, non-commutative polynomial functions, non-commutative polynomial Q, and non-commutative variables, polynomial transformations, non-commutative expand, and non-commutative collect, Grosvenor bases. So we have non-commutative Grosvenor bases, non-commutative polynomial reduce, and non-commutative monomial list. And some related functions, generalized power, commutator, and anti-commutator. So first, let me talk about algebra representation. A non-commutative algebra object represents a unitary algebra. It is used in non-commutative polynomial functions to specify the names for algebra operations, neutral elements of addition and multiplication, variables that are assumed to represent scalars, and variables that are assumed to represent commutative elements of the algebra. Other variables are assumed to represent non-commutative elements of the algebra. So an algebra is a vector space equipped with a bilinear product operation. An algebra is unitary if its product operation has a neutral element. So let us create an algebra with default setting. So we don't need to give any arguments to non-commutative algebra. And we got an algebra with multiplication given by non-commutative multiply, addition given by plus, unity represented by 1, 0 represented by 0, no commutative variables, no scalar variables. So the default multiplication operation is non-commutative multiply, which is entered as 2 asterisks. So x non-commutative multiply y is entered like this, and this typeset as this sign. And here are some other special algebras that we have defined. So this is not non-commutative algebra of n by n matrices. So the multiplication is represented by dot, unity is represented by identity matrix, and 0 is represented by 0 matrix. Here is non-commutative algebra of linear endomorphisms with composition. So multiplication is given by composition, and unity is given by identity. Tensor algebra. Now multiplication is tensor product. And we can also give completely symbolic names for the algebra properties. So we can call multiplication mult, addition add, unity 1, and 0 is called 0. And here's how to extract the property value of an algebra. So this extracts unity from the previous algebra. Now let's talk about non-commutative polynomials. So here we define a polynomial in the default algebra. So multiplication is non-commutative multiply. We can find the variables in this polynomial, check that the polynomial is actually polynomials in these variables. And unlike in the commutative case, P is not a polynomial in a subset of variables because Z is not an element of the coefficient field. So if we ask whether P is a polynomial in XY, it's false. On the other hand, if we declare that Z is an element of coefficient field, so we say z is element of scalar variables, and now it is a polynomial in x and y. We can expand the polynomial p. As you can see, we got this in the result. This is generalized power of non-commutative multiply. So let's see the input form of this is generalized power, the operation x, and it's a second power. And as you can see, second power of x is the same as x non-commutative multiply with x. Now let's expand P over the algebra where z represents a scalar variable. So you can see that z was now pulled out in front of the terms, and it's multiplied with using times, regular times, not non-commutative multiply here. And here is a regular square of z rather than generalized power. And this expands the same polynomial with z now declared to be a commutative variable. So z was pulled out in front, but it's multiplied with the rest of the term using non-commutative multiply. And here we get a generalized power of z rather than just regular power. Now let's talk about collecting terms in a polynomial. So let's define a polynomial. Now collect with respect to x on both sides. So here x was pulled out on the right, here it was pulled out on the left, here on the right. Now let's collect with respect to x only on the left. This collects only on the right. Here this collects with respect to x on both sides, but first on the left, then on the right. So by default, it's first on the right. Here we specify that we want first on the left. So you can see each time we get a different result for this polynomial. And here is collection with respect to multiple variables in different order of collecting. We collect with respect to x only on the left, or and here on the right. Again, each time we got a different result. Now let's talk about non-default algebras. So this is the algebra of n by n matrices. And we can do expand. Now this expands dot with respect to plus. Now algebra of linear endomorphism is composition. Again, we can expand composition of sums of endomorphisms. Tensor algebra, we expand tensor product. And we can do it in an algebra with completely symbolic property names. So let's define the algebra with multiplication mult and addition add. And we now expand mult with respect to add. We can also collect over this algebra. And we can see that subtracting the last two results, since they are two different forms of the same polynomial, will give 0, and we get the named 0 of this algebra. Now let's show commutator and anti-commutator. So here is a commutator of two variables. By default, we use the non-commutative multiply as multiplication. This gives anti-commutator. This gives commutator in the matrix algebra, so we specify the algebra here. Now let's prove some commutator and anti-commutator identities. So this is the Jacobi identity. And we can use non-commutative expand to prove it. And here is another identity, Leibniz rule. So let's again prove it with non-commutative expand, take the difference of both sides, expand, and we get 0. And here is an identity that connects commutator and anti-commutator. So this expression using commutator and anti-commutator is 0, which we prove using, again, non-commutative expand. Now, before we can talk about Grobner basis and polynomial reduce, we have to talk about monomial orderings. So a multigrader lexicographic monomial order is given by a list of lists of non-commutative variables. So the monomials are ordered first on the number of occurrences of variables from the ith list, with the smallest I for which the numbers differ, then on the number of occurrences of the commutative variables. If all number of occurrences are the same, monomials are ordered lexicographically on non-commutative variables and then lexicographically on commutative variables. Non-list elements in the top list are equivalent to one-element lists. So, for example, per xy is equivalent to per singleton x and singleton y. Here, for multigraded lexicographic monomial orders for bivariate monomials. So here is a polynomial of degree 3 in 2 variables. And let's see how the monomials are ordered using different monomial orders. So here is the monomial order singleton x singleton y. Here is the monomial order given by per xy. See, the order of these terms is different here. And we can have, if we reverse the order of y and x, we also get different orders. So these are, for 2 variables, we have just 4 possible orders. So now we can talk about Grobner basis. So let's compute a Grobner basis of a 2-sided ideal in a non-commutative algebra. So here are the polynomials that generate the ideal. And here we compute the Grobner basis. Now we can reduce this a polynomial x times x modulo this Grobner basis. So here is non-commutative polynomial reduce. It gives the output similar to what we get from polynomial reduce, except that polynomial reduce gives, the first element just gives coefficients by which we need to multiply Grobner basis to get the original polynomial. Here we get linear functions because in the non-commutative case, there are many different kinds of linear functions depending on the position in which we multiply by the variable. So here we multiply on the right, here we multiply on the left. We cannot pull it out, the variable. And so we get the coefficient linear functions and we get the reduced result, where we eliminated, in this case, the first 2 variables. And here's how we get the original polynomial. We apply functions to the Grobner basis, the linear functions to the Grobner basis elements. We add the remainder. And indeed, we got the original polynomial, x times x. And also, unlike in the commutative case, a non-commutative Grobner basis may be infinite. So for this set of polynomials, the Grobner basis is infinite, and non-commutative Grobner basis has a limit on the number of iterations that can be set using an option, max iterations. So by default, it's 50. After 50 iterations, we didn't get a Grobner basis. As you can see, that there is a certain pattern where you can have arbitrary power of x here between z and y. And however, with the same generators but different monomial ordering, a finite Grobner basis may exist. In this case, we get a quite simple Grobner basis if we treat y and z as a pair here. So it's a different graded monomial order. Now let me show an application of Grobner basis. So we can show that the Woodbury matrix identity, here it is, quite commonly used, is true in arbitrary algebra and requires only the minus first power to be an inverse. So as we will show that it actually doesn't applies in arbitrary algebra. It doesn't have to be matrices. So to stress this, let's replace dot with non-commutative multiply and inverse with symbol inv. Now find all the inverses that are present in this formula. Now add relations that need to be satisfied by all inverses. So as you can see, it has to be left inverse and right inverse. These are two separate relations that we need to add. Now we compute a Grobner basis of the relations with the inv variables made larger than the other variables. So we can eliminate them. And we compute the Grobner basis. And now we show that the difference of both sides of the identity reduces to 0. So we have proven that the identity is true for any algebra. And this is all. Thank you for listening.
Welcome to the matrix functionality section of the What's New in 14.3. Here I'm going to present the several functions that we have introduced related to either matrix or linear algebra more generally. This is part of an ongoing effort. In this release, we have between 12 and 15 new functions, I believe, and we plan to release around the same amount in the next release. The slides will have more detail than what I will cover verbally, and they have links to documentation that cover yet far more detail than the slides themselves. We have introduced the companion matrix as a specialized type of matrix. And what that is given a set of numbers, which are typically the coefficients of a polynomial, we set them, the standard method is to set them, negate them, and have them running down the main diagonal from the 0 degree to the n-1 degree coefficient of a polynomial, and then we have ones on the the subdiagonal. There are, however, other ways to format it using the directives left, top, bottom, right is the default here. And these are important because they are the components of what's called the rational normal decomposition of a matrix, typically a matrix of rational numbers. I won't go into too much about that now, but we'll cover that in a later slide when we go over the Frobenius decomposition. Okay, so that's one new matrix type we've added. Another is the Jordan matrix. And here we have, for a given value and a dimension, so V is the value, dimension 4, we have that many V's going down the main diagonal, and then ones on the super diagonal. And alternatively, we can reverse that placement. These are components of what's called the Jordan decomposition. This is a function we've had roughly since forever, at least going back to the early to mid 90s. And so They're in a way similar to this is in a way similar to the companion matrix. The Jordan matrix gives the building blocks of the Jordan decomposition. The companion matrix gives the building blocks of the rational or Frobenius decomposition. And again, we'll see more about that later on. Okay, another function that we've had internally for a long time and finally saw fit to make into a full-fledged system function is the matrix polynomial value. What this is we give a matrix and a polynomial, not surprisingly, and we evaluate the matrix at that polynomial. So for a simple 2 by 2 matrix here, and the polynomial whose coefficients are 1, 2, and 3, meaning 1 plus 2x plus 3x squared, we evaluate the matrix. It is 1 times the identity matrix, the 0 degree, 2 times the matrix itself, plus 3 times the matrix dotted with itself, effectively squared. And here I just show in this example that this comes out to the same as if we expanded this in a very pedestrian way using matrix powers. And this is a slightly sicker way of redoing that at the bottom here. And they all give the same result, as you would expect. So matrix polynomial value is a concise way of requesting that evaluation. The range space, well, I won't say too much about this. It is what it says it is. It's the span of the columns of a matrix, if you think of them as vectors. And, well, I give a couple of brief examples. It's a nice thing to have because sometimes you want to know the span of the column space, and this is a direct way now to get it before you had to do some linear algebra. Okay, eigenvalue decomposition. This is effectively a repackaging of eigensystem. It's a convenient one, however. When a matrix can be diagonalized, you have a transformation matrix, which I call T, and its inverse, and the matrix can be rewritten as T times this diagonal form times the inverse of T. And you can get the T and that diagonal through the eigensystem, but it's not conveniently packaged in this way. The eigenvalue decomposition is a special case, but the most common case, of the Jordan decomposition. You use the Jordan decomposition, you have to, when you cannot diagonalize the matrix, but in some sense, most matrices can be diagonalized, and then the eigenvalue decomposition is a nice, convenient way to get that diagonal form. Okay. Let me back up a step. This blue means I put in a link to the documentation page. And I thought all of these were blue. Apparently, I missed the link here. So before I release this notebook, I will repair that. The polynomial Hermite decomposition is the same as the ordinary Hermite decomposition in a sense, except the ordinary one works with integer matrices, whereas this works with matrices that have polynomial entries in some variable, one variable. And the idea is similar. You're doing Gaussian elimination, more or less, except you cannot take fractions. If you remember your linear algebra, you divide by pivots to make pivots equal to 1. We can't do that kind of division here. What we use instead are polynomial greatest common divisors. Just as with the integer case, we use integer greatest common divisors. And we still get an upper triangular matrix. So it's not, in some sense, as reduced as if we could use fractions, but the advantage is you remain in the algebraic structure in which you started. In other words, polynomials in this case. We don't create fractions of polynomials, also known as rational functions. And so here's some examples. And again, we give a conversion matrix U and the Hermite form itself, H, And you'll see from that Hermite form, this is it, that it's got something very convenient in the first element, which is what we call a unit, in other words, a constant polynomial, and then below that a zero. So it's upper triangularized. There are some nice applications of this function. And these, again, the blue is a link to the example itself in the documentation. And so, check there for further details. As with the integer Hermite decomposition, there's also a polynomial, I'm sorry, an integer Smith decomposition. And it's the same with the polynomial case. Here we actually diagonalize the matrix because we allow now transformations on both sides, the left U and the right side V being the transformation matrices. And the middle matrix S here is the diagonalized form, and you'll notice that it actually is just constants, and that's fairly typical. It doesn't always happen that way, but that's a common enough case. And so this is a really convenient form. And again, we stay with just polynomials. There are no fractions, no rational functions. Okay. Another wrinkle to this, though, is we actually allow rational function entries because they're quite useful in computing what's called the Smith-Macmillan form. And that has applications in control theory, for example. There's an example of it in the documentation. There are other applications as well. And again, there's examples with links there. Okay. We have made some convenience functions because sometimes people don't want the decomposition. They just want what's called the normal form. So there's the Hermite normal form, the Smith normal form, etc. And sometimes it's even cheaper to compute when you're just computing the normal form and not also having to compute those transformation matrices. So there's some efficiency and sometimes even less memory consumption when we can take shortcuts and just give the normal forms themselves. And so we now do that for Hermite, Smith, the polynomial Hermite and polynomial Smith normal forms. Now, why do we call this Hermite reduced instead of Hermite normal form? Well, simply enough, form functions in the Wolfram language usually refer to formatting, input form, standard form, etc. So we opted instead to use reduce because they're, in a sense, reductions as well as being normal forms. Oh, and I did provide, I mean, essentially they're all similar, but I provided a simple example here. And the matrix normal form for this matrix is, well, here it is. And we just show that you get the same from the Hermite decomposition, taking the second element. This is a function that we have considered for off and on for a long time, the matrix minimal polynomial. What is that? Well, if you remember linear algebra, there's the characteristic polynomial, which is fairly simple to evaluate and which we have a function characteristic polynomial. And well, a fact from linear algebra theorem is that if you evaluate the matrix itself at its characteristic polynomial, you'll get the zero matrix. But sometimes there's a lower degree polynomial for which that happens. It's a divisor of the characteristic polynomial, and that's the matrix minimal polynomial. Now, sometimes they are equal up to a constant factor, but sometimes one has strictly lower degree. So here's a 2 by 2, and if you remember your linear algebra, the characteristic polynomial has to have degree 2. As it turns out, so does the minimal polynomial, so they agree, again, up to a constant factor. And just to show, when we evaluate using this new matrix polynomial value function, we do get the zero matrix. And here's a case where we have a 3 by 3, and yet the minimal polynomial is of degree 2. So it is strictly smaller than the characteristic polynomial, and one can check it divides the characteristic polynomial. Okay, an advantage here is that well, a nice thing is that we can work with matrices modulo a prime and with matrices containing elements that live in an algebraic extension field. So that's a kind of nice thing to be able to do sometimes. Frobenius decomposition. So this has a history. This is something we've wanted to implement for about 30 years. And people would ask me about that, and I would tell the truth. I don't know how to do that. And finally, basically got the directive, well, okay, maybe it's time to go figure it out. So I did. And I downloaded some course notes and some papers and put together this function. What is this? It's like the Jordan decomposition, as I said earlier, but and it does return a transformation matrix and a Frobenius normal form, which is a block diagonal matrix. And on those blocks are comprised of companion matrices, as I mentioned somewhat earlier. And these companion matrices are related to both minimal and characteristic polynomials, and I won't go into the details there, but it's convenient. Well, the Jordan decomposition will take the matrix to an almost diagonal form, sometimes to a fully diagonal form if it's diagonalizable. But it introduces algebraic numbers, algebraic extensions. And these can be very complicated, radicals or root objects, and it can be slow to compute working with those. And what you get can be a real mess. And the characteristic polynomial, I'm sorry, the Frobenius decomposition has the convenience that it only works in the field in which you start off. So if your matrix has rational numbers for entries, then the result will as well. You do not have algebraic numbers. You do not have root objects. You do not have anything that's going to be difficult to compute with. Another advantage is that we can handle a prime modulus now. Jordan decomposition, which I should have linked to here and will, doesn't do that. It's in theory, one can do that when working with a prime modulus because you can define algebraic extensions, mod primes. It's a well-known thing in university algebra courses, but then there's some ambiguity of how they're defined, and you have to set up some amount of notation, and it's just not something that would be more trouble than it's worth, frankly. And the users wouldn't much care about. So anyway, Frobenius decomposition, though, handles a prime modulus just fine. Okay, we're getting towards the end. So those were the new functions. We've also updated a couple of functions. Projection. We have always been able to project a vector onto a vector. Now we can project onto a vector space. You give a set of spanning vectors. So here I give these two vectors and I say, project this guy onto that space. And lo and behold, we can do it. What happens? You get the 1 and the 2, the 3 gets clipped off because this space doesn't have any z coordinates that aren't 0. It's not usually that simple. The projection usually gives something a little more complicated, but I chose a simple example. Singular value decomposition has also been upgraded to take the thin form. This is something fairly standard from the literature. And what's nice about it is it can give a more concise result. So if you have a matrix with one, say, a tall, thin matrix or a short, fat matrix, so the dimensions are very different, your singular value decomposition is going to have whichever the larger dimension is, you're going to have a transformation matrix of that dimension. And that can be inconvenient because of necessity, it can only have the highest maximal rank it can have is that of the smaller dimension. That's how matrices work. And so I'll show an example here, but I picked an 8 by 5, which is taller than wide, although not by a huge amount. I find the singular value decomposition, and I get this 8 by 8 here, and a 5 by 5, which is a smaller dimension. And then I get the singular values, the non-zero ones, there's 5 of them, and the rest are zeros because it only has rank 5. And so that's how it is. But with the thin case, we don't have to go 8 by 8. And in fact, we only have to go 8 by the rank, and the rank is 5, so 8 by 5. And we only keep 5 of these, the rank, again, so the non-zero singular values, and then it's the small matrix that gets repeated. So think if instead of 8 by 5, it had been 80 by 5, well, the savings would be, instead of having an 80 by 80, we'd have an 80 by 5 matrix on the first transformation matrix. And that's a huge savings in memory. And then figure, okay, many problems that call for singular value decompositions use matrices with dimensions in the hundreds or even thousands, and sometimes with low rank. And those are cases where you'll have huge savings in memory. And also many functions now take a target structure option. Some did in 14.2 as well. I won't go into the details on that here. It's all going to show up in the documentation for the new functions. Okay, so that was everything. And again, there'll be another 12 to 15 new functions in the next release. And so we'll cover those when that comes out. So thank you very much for your attention.
Hello everyone, I'm Martin from the Wolfram Research Numerics group, and now it's time to discuss what new features we have for fluid dynamics in the newest version of the Wolfram language, 14.3. But before we start, there's a couple of links I would like to show you. The first link goes to our Wolfram Core RFM page. This is a web page that features all the overview of the things that we have for the finite element method. So if you would like to solve some star solving problems with the finite element method using the Wolfram language, this is a good place to start. The second link is the PDE models overview page. This is a part of the documentation, and it gives an overview of all the PDE models that we have that are currently implemented for the Wolfram language. So acoustics, electromagnetics, fluid dynamics, which we are going to discuss today. It features links to the monographs and examples, both examples that serve as an introduction or more advanced examples. The last link is the laminar flow monograph, because today we are going to discuss fluid dynamics, and this is our monograph for the fluid dynamics. It features many examples and also discusses the theory, like what is a Newtonian or non-Newtonian flow, and the equations of the fluid dynamics. So if you are kind of familiar with the finite element method in the Wolfram language and would like to start exploring fluid dynamics, this is the place to start. So now let's go back to the new features in the Wolfram language, and the most important feature for fluid dynamics that we have in the new version is the axisymmetric flow. So this is what we are going to discuss in this talk. But since I'm not sure if all of you are familiar with the fluid dynamics, I would like to start from the Navier-Stokes equations, which are the most important equations in the fluid dynamics. So the Navier-Stokes equations are named after a French engineer called Louis Navier and Irish physicist George Stokes, are partial differential equations that describe motion of a viscous fluid. Here we can see them in their incompressible form. and it's a system of equations where the unknown represents the velocity, which is here, v, and the pressure, p. The pressure p is a scalar, and the velocity v is a vector valued function, and which has 2 components in 2 dimensions and 3 components in 3 dimensions. So in total, you have 3 or 4 unknowns depending on the number of dimensions. The g here represents some gravity or any other external force, and it's something that's sometimes neglected or omitted. Mu here is the fluid viscosity, and rho is the fluid density. As you can see, those equations are kind of quite complicated, so writing them on your own would be quite difficult and annoying. So that's why in the Wolfram language we have the fluid flow PD component, which models a fluid flow of a viscous fluid. Here we can see an example for how we can use the fluid flow PD component to generate the stationary Navier-Stokes equations in 2D. So the fluid flow PD component takes 2 parameters, 2 arguments. The first argument is the variables. So here we have u, v, and p. U and v are the components of the velocity, only 2 components because we are in 2D, and the p is the pressure. And since we are in only 2D and we are dealing with stationary equations, they only depend on x and y. The second argument of the fluid flow PD component is the parameters. So here we have the dynamic viscosity and the mass density. And that's basically it. So this is how you can use the fluid flow PD component to generate and model the flow of viscous fluid. So now let's go to the new feature in the 14.3, and that's the axisymmetric flow. But before we start with axisymmetric flow, I need to introduce the cylindrical coordinates. The cylindrical coordinate system is an alternative coordinate system to the more common Cartesian coordinate system, and instead of describing a position in a space with x, y, and z, we use r, theta, and z. The z stays the same, and so we only replace the x and y by r and theta. R represents the distance from the z-axis, and theta represents the angle. And that's it. It's kind of simple. So instead of using x and y, and like here, we just use the angle and the distance from the z-axis. And those are the cylindrical coordinates. Here we can see the incompressible Navier-Stokes equations in the cylindrical coordinates. And as you can see, those equations are quite complicated. So that's why if in some cases we can actually simplify those equations by assuming that we are dealing with axisymmetric flow. The axisymmetric flow depends on the assumption that the domain and that the flow and the domain we are dealing with are axisymmetric. That means that if we rotate the domain around the z-axis, it won't change. So here is an example. Rotating this domain around this z-axis won't change anything because the domain is invariant with respect to rotations around this z-axis. So with this assumption, we can assume that the flow does not depend on the angle. So all the derivatives that are here, like for example here, with respect to the angle, are now equal to 0 because the velocity does not depend on the angle, and also the angular component of the velocity is now also equal to 0. So this way we can simplify the system of equations into the following form, where, as you can notice, we now only have 3 equations instead of 4. So this means that solving the system of equations will take less time, and we will need less memory. So this is a great thing to do because it's very practical. And so now let's see an example in the Wolfram language. The first example that we have here is the stationary flow in the cylindrical pipe with a three sections, and the flow in the pipe is driven by a parabolic inflow. So this is the domain in 3D. This is this kind of cylindrical pipe, and as I've already mentioned, it has these three components basically. So as you can see, this domain is symmetric around this z-axis. So we have an axisymmetric domain, so we can simplify the equations to obtain two axisymmetric equations to reduce the time and memory that we need to solve the equations. So the first thing we do is that we create the axisymmetric 2D domain. So this is this kind of domain, and if we would rotate this domain around this axis of symmetry, which is this edge, then we would obtain this full 3D domain. So, and this axisymmetric 2D domain is the one we are going to work with. So the first thing we do is then we specify the variables. Since we are dealing with axisymmetric problem, we assume that the second component of the velocity, the angular one, is equal to 0. So that's why here we have the 0. And the other components of the velocity, u and w, and the pressure, they do not depend on the angle theta. They only depend on the r and z. Next, we specify the model parameters. So we have here this dynamic viscosity and mass density, and here we have one additional important parameter in this region symmetry, which is set to axisymmetric. And that's basically it. This is all you have to do if you want to deal with axisymmetric, or if you want to obtain axisymmetric Navier-Stokes equations. All you have to do is just to modify slightly the variables and set the region symmetry to axisymmetric. The fluid flow PD component takes care of the rest. Since we are dealing with PDEs, we need to set up the boundary conditions. So the first boundary condition here is this parabolic inflow, so this is an inflow here at the bottom of the domain, and this is what drives the flow in this domain. Second boundary condition is a no-slip boundary condition on the wall. This means that we assume zero velocity here at this wall. So since the velocity is equal to 0, this means that the fluid sticks onto the boundary of the domain, and there is no slip. That's why this boundary condition is called no-slip boundary condition. Next, we have outflow boundary condition and also this axisymmetric symmetry boundary condition, because we do not want to have any flow across this axis of symmetry. And the last boundary condition that we have is this boundary condition for pressure, because otherwise we would have infinitely many solutions. So fixing this pressure at one point gives us a unique solution. Next, we combine the boundary conditions into one variable and solve the equations with ND solve value. Here, I would like to point out this interpolation order. So we set u and v, u at w to 2. This means that the velocity components will be piecewise quadratic, and the pressure will be only piecewise linear. This is what's known in the fluid dynamics as a Taylor-Hood finite element, and it's very common and probably the most common, most popular finite element that's used in the fluid dynamics. Now here we have some visualization. So this is the solution plotted using the vector plot, and here we can see a nice vortex that appears at this part of the domain. In the stream plot we can see basically a similar behavior. And the last plot that we have here is the contour plot for the pressure, and we can see a pressure drop in this the largest part of the domain. So even though we were actually dealing with a 3D problem, we reduced it to just 2D because thanks to the axisymmetric assumption. But at the beginning we started with a 3D problem. So here we have a visualization of the solution in 3D using the stream.3D. A second example that I have here is time-dependent flow in a cylindrical pipe with a narrow middle section, and now it will be driven by pressure gradient, not in the flow. So this is the kind of domain that we are dealing with. Here on the left-hand side we have once again the axis of symmetry. So rotating this 2D domain around this edge would give us the fully 3D domain that in which yeah. So the first thing we once again do is we specify the variables, and here is the same story, but the only difference is that we have this t, because now we are dealing with time dependent problem, so the velocity and the pressure now also depend on time. But the second component of velocity is once again set to 0, and none of the velocity components or the pressure depend actually on the angle. So it only depends on time, r, and z. Once again, we specify the model parameters, where we have this important region symmetry set to axisymmetric, and now we have the boundary conditions, and we generate the we use the fluid flow PD component to generate the equations. So the first boundary condition that we have is once again the no-slip boundary condition here on the wall. So we assume that the velocity is equal to 0 at this part of boundary. The second boundary condition is this inflow boundary condition, and which is then followed by this axisymmetric symmetry boundary condition, because once again we do not want to have any flow across the axis of symmetry. The last two boundary conditions are boundary conditions for pressure, because this flow will be driven by a pressure gradient. So what we do is that at the bottom, at the inflow of at the bottom of the domain, we slowly increase the pressure, which creates a pressure gradient in the domain, which will then drive the flow. And then we of course combine the boundary conditions into one variable, and since we are dealing with time-dependent problem, we also have to prescribe the initial condition. Then once again we use the ND-solve value to solve the equations, and once again we have this Taylor-Hood finite element. Here we can see the solution plotted using the vector plots. So this is how the solution, this is how the flow looks like at various times. We can see a vortex that starts to appear. In this part of the domain. Next, what we have here is the outflow profile, velocity profile of the flow. So this means that this is the velocity profile here at the top of the domain. The last plot that we have here is the plot for the pressure. So here we can see how the pressure gradient forms. So that's it. That's basically how you use the fluid flow PD component to model the axisymmetric flow. And as you can see, it's fairly easy. The only difference from the standard Cartesian Navier-Stokes equations in the Cartesian coordinates is that we slightly modify the variables, and we add the region symmetry set to axisymmetric. So modeling axisymmetric flow is very easy, used in the Wolfram language. Another new thing what we have for the fluid dynamics in the newest version of the Wolfram language is that we have new monograph, which is called the Fluid Dynamics Verification Tests. This monograph features 5 common benchmarking tests with references, which verify that our fluid dynamics framework produces correct and accurate results. The first benchmark is a stationary 2D flow around a cylinder. This is a very common benchmark in fluid dynamics, and the goal of this benchmark is to compute a traction and the lift acting on a cylinder. The second benchmark is the lid-driven cavity, also stationary, and this one also features non-Newtonian fluids. The third and the fourth are axisymmetric flows in a cylinder. One is stationary, the other one is time-dependent, and this is a comparison with the exact solution. And the last benchmarking test is a time-dependent flow in a cube, which is once again a comparison with an exact solution. So to summarize all this, the new feature in the newest version of the Wolfram language is that now the fluid flow PD component now supports the axisymmetric flow, which allows us to transform a 3D problem to 2D by exploiting the symmetry of the domain, which saves both time and memory. It's very useful for dealing with flows in pipes and similar geometries. You can find examples of this axisymmetric flow in laminar flow monograph, in the fluid flow PD component ref page, and also in our brand new fluid dynamics verification tests monograph. I hope you have learned something new, and if you have any questions, feel free to ask.
Hello everyone, and thank you for joining. Today, I'll be taking you through what's new in System Modeler 14.3. You're already familiar with Wolfram Language as a platform for data analysis, visualization, and computation. But what if we could extend that same power into engineering systems, like solar PV plants, electric vehicles, or building HVAC systems? That's exactly the role of System Modeler. I'm Ankit from the Wolfram System Modeler team, and I will walk you through some of the new possibilities. As we enter the age of renewables and smart connected systems, some challenges emerge across industries. Systems aren't standalone anymore. An electric vehicle is also a powertrain, a battery, a thermal system, and a software stack, all tightly coupled. Every design decisions now has to balance performance with energy efficiency, emissions, and long-term environmental impact. The pressure to deliver faster means we need tools that shorten prototyping cycles and reduce manual work. Real world conditions like weather, usage patterns, or supply variability are unpredictable, but designs still need to perform reliably. These four challenges complexity, sustainability, speed, and uncertainty are what defines modern engineering. And the question is how do we design systems that don't fail under these pressures? Let's flip that challenge around. What if we could design in a way that anticipates these uncertainties? What if we could validate thousands of scenarios automatically, build models of microgrids or HVAC systems quickly with ready made components, iterate on designs faster with live tuning, and collaborate seamlessly across teams? That's the vision driving System Modeler 14.3. Let's see how it comes to life in the new capabilities and libraries that we have added. Let's start with the first challenge, designing for reliability under uncertainty. Testing a single scenario is easy, but in reality, a design must perform across all conditions, like different drive cycles, weather, and vehicle loads. Here is an EV thermal management model. Imagine you are the thermal engineer responsible for keeping the battery within safe limits. Let's open the model in System Modeler. Here, you can see the battery connected to its cooling system. We will link this to a drive cycle and simulate the thermal performance. The plots show three things: the velocity profile of the car, the battery current, and the battery temperature. There are there are clear requirements on the design that the battery current must stay below 200 amperes and the battery temperature must not remain above 25 degrees Celsius for more than 4 minutes. In this first simulation, the results look okay. Current is within limits, and although the temperature goes above 25 degrees Celsius, it doesn't stay there long enough to break the requirement. But this is just one scenario. Let's get back to the presentation. What we saw in System Modeler was just one scenario. But what about real world conditions? Stop and go traffic, hot summer days, or carrying heavy loads. Running all these cases manually is tedious, and analyzing whether each one passes requirements usually takes a lot of scripting. With version 14.3, we have introduced a requirement specification language with functions like system model validate. This let you validate designs directly against performance and safety requirements. Using these functions, you can check behavior over time, manage uncertainty, and detect edge case failures early in the design process. Here's how it works in our EV example. You could always run thousands of simulations in parallel using system model simulate, each with different drive cycles, loads, and ambient conditions. For this presentation, let's look at 50 scenarios. Now, with version 14.3, we can express requirements directly using functions like system model always. We encode conditions such as battery temperature must not exceed 25 degrees Celsius for more than 5 minutes. And we will start evaluating only after 300 seconds to skip startup effects. We then pass these requirements to system model validate. This function checks the simulations and reports the results. In this case, one test failed. The system also records where, when, and under which configurations failures occur, so you can trace them. Here, the failure is in the China drive cycle. The failure plot shows the battery temperature staying above 25 degrees Celsius for over 4 minutes. In practice, this replaces hours of manual validation with a single function call, delivering insights much earlier in the workflow. So, to summarize of what this means in practice, I can simply run the EV drive cycle model, provide a list of drive cycles and operating conditions, state my requirements like current and temperature limits, and tell the function to report all violations. That's it, one function call. Suddenly, I validated my design across thousands of scenarios without writing custom scripts for each case. And here's the big shift. Engineers can now spend their time making design decisions, not building validation code. This saves enormous amount of time, so what used to take hours now takes minutes. More importantly, it can transform the workflow. You can validate you can validate much earlier in the design phase. You can test far more scenarios than before, and you can build safer, more reliable systems because problems are caught automatically. That's how System Model 14.3 addresses the first challenge: safe, reliable design under uncertainty. Next, let's move on to the second challenge, that is energy systems and the climate transitions. Energy systems today must integrate renewables, grids, and buildings with rooftop solar, and they have to do so reliably. The problem is that building these models from scratch is often slow and complex. That's why System Model 14.3 introduces support for energy libraries. The photovoltaic library for PV and grid integration, the power grids and power system libraries for transient grid modeling, and the IBPSA buildings library for designing HVAC systems. Together, these libraries let you model not just one component but the entire ecosystem, from rooftop solar all the way down to heat exchangers, pipes, and valves to model HVAC systems. Let's look at an example. Let's say you are a HVAC engineer who is tasked with maintaining thermal comfort in a room of height 3 meters and width 6 meters. Your job is to keep indoor conditions comfortable, ensure good air quality, and minimize energy consumption in a building. There are two things you have to design. How should the HVAC system, including the flow rates, pump sizes, and heat exchangers, be designed? And how should the inlet and outlet ducts be placed to ensure even airflow inside the room? Let's answer the first question. With the IBPSA library, you have access to the components such as fans, pumps, ducts, and heat exchangers that you can readily use and build a full system model. In this case, air from the ambient is heated through a heat exchanger, then cooled using another heat exchanger, then sent to the room. In heat exchanger 1, the outlet air from the room is used to heat the inlet air, whereas in heat exchanger 2, water is used to cool the air. And once this model is built, you can immediately start simulating how the building behaves under different conditions. You can control the air inlet velocity, water mass flow rate, and track the room temperature along with the carbon dioxide levels in the room to maintain comfort. Now, let's answer the second question, duct placement. We can use the system model for boundary conditions and then apply FEM in Wolfram language to simulate airflow and pressure inside the room. Let's look at scenario 1 where the two ducts are pointing downwards. Velocity plots show strong jets hitting the flow, creating uneven circulation. Pressure is high near the inlets but drops off in the back. And in scenario 2, when the ducts are pointing sideways, velocity distribution is smoother, mixing is more even, and pressure is balanced across the room. Now, as a HVAC designer, you can clearly weigh the trade-offs. Downward ducts are cheaper to install but less effective. Sideway ducts improve comfort but require more ductwork and cost. With System Modeler and FEM, you are able to compare these design options directly. So, for an HVAC designer, this workflow changes everything. You can model the entire system from pipes and heat exchangers to airflow in a single room. You can compare multiple designs quickly and make informed trade-offs. And you can communicate results visually, making it easier to align with architects, managers, and clients. So that's the second challenge, tackling the climate and energy transition by making energy systems easier to design, test, and optimize. Our third challenge is iteration speed. Imagine you are a solar design engineer tasked with configuring a rooftop's PV system. You need to decide how many modules to connect in series, how many to connect in parallel, and how the system performs under different configurations. Let's open the model in System Modeler. Here you see a solar plant connected to a fixed load. If we simulate this model, we can examine how power, voltage, and current change as we vary the number of modules. Traditionally, exploring different configurations meant stopping and restarting the simulation for each parameter set. With version 14.3, we can do this differently. We can run a simulation once in real time, adjust parameters like number of series modules or parallel modules in real time, and instantly see the impact on power output and electrical characteristics. We can even track parameter history and compare multiple configurations all in a single run. For a rooftop solar engineer, this means less time waiting and more time designing and optimizing. There is another new feature in 14.3 that makes results much more intuitive. That is calendar time in simulation. In earlier versions, results were always shown in generic simulation time, that is seconds, minutes, or related time units. That makes it hard to connect to real world performance. With version 14.3, you can now enable use date and time option in settings, and this lets you anchor your simulation to a specific calendar date. Let's get back to our presentation notebook. The same calendar time simulation applies in Wolfram language. When plotting results, you can set an epoch. For example, you can set the start on January 1st, 2015, and even bring in real solar irradiance data from databases like PVGIS, and then run the PV model across the entire year. The outputs are plotted directly on a calendar scale, so you can immediately compare performance in winter versus summer. This makes it easier for both engineers and stakeholders to connect simulation results to real world experience. So, what does this mean to our solar design engineer? They can configure rooftop systems in real time without endless restart cycles, track the history of their design adjustments as they go, and evaluate system performance across an actual calendar year. This accelerates prototyping cycles, makes iterations more intuitive, and leads to better design in less time. So, there's a third challenge: faster iteration and deeper insight through live tuning and calendar time simulation. So, beyond the three challenges, System Model 14.3 also includes some smaller but very practical improvements. One improvement is that you can modify an icon based on the parameter values. For example, in this process plant model, the color of the tank depends on the temperature of the fluid. That means you can see configurations at a glance and spot errors directly in the diagram without digging into the code. Another big help for collaboration: the underlying Modelica code is now Git friendly. So formatting is cleaner and diffs are easier to read, and version control flows more smoothly. For larger projects, this saves a lot of time in reviewing and merging changes. This might sound like small details, but they make a big difference. You can catch configuration issues earlier before they become costly, and collaborate more smoothly with colleagues thanks to a cleaner version control. So, in summary, with System Model 14.3, we have seen how you can build safer designs under uncertainty by validating thousands of scenarios, model climate and energy systems more easily from rooftop solar to airflow in a single room, and iterate faster with live tuning and calendar time simulation. On top of that, you also got practical improvements for visualization and collaboration, like configuration aware icons and grid friendly formatting. If you'd like to explore more, the What's New page gives a deeper dive into the new features. And the System Modeler overview page is a great place to start if you're new to System Modeler. I invite you to explore these capabilities and see how they can fit into your own projects. Thank you.
Thank you very much, Ankit. And that brings us to the end of this wonderful series of talks. And I think that it'd be great if we could actually have a little bit of time for discussion. We are running short a little bit, so I think we should try and wrap up soon. But what I think I'll do is to just quickly let everyone have a chance to talk about their favorite topic in today's webinar. And I know that about the homotopy method, Danny had some ideas about Clifford algebras. Adam had something to say. I'm sure Oliver is hoping to say something about turbulence, and Ankit about something, but in the system modular context. So let's just go around and let people have a chance. So maybe we should begin with Adam. Anything from you, Adam?
Okay, so there have been some questions about some special algebras, like Clifford algebras mentions there. So let me just mention that the non-commutative algebra is still under development, and in the next version we will have more built-in special algebras. In particular, we will have algebras with built-in relations. So just using expand will put the algebra element in will do all the arithmetic operation within the algebra, including the relations that define the specific algebra. Right now, the version 14.3 basically has 3 algebras, and if you want relations, you have to manually use Grobner bases and polynomial reduce to handle them. But there is more coming. So that's what I want to say.
Great. I think Adam's been working really hard. It's deep work, I think, from Lewandowski. It's I mean, like reading like a PhD thesis and trying to put it into code is not easy, but Adam is almost there, so he tells me, So the next version should be a very exciting version where we bring in all the things that people talk about in physics, Clifford algebras and Dirac algebras and that kind of stuff. So that's what's on over there. Danny, anything from you? You had something about the homotopy method, or something else that you want to mention? Go ahead, please.
Well, I don't have too much to say about it. It's been a while since I've looked at literature involving that, but there are a few sort of hybrid symbolic numeric approximation methods out there for working with differential equation systems. One is a Domian decomposition, then one is this hybrid I think HAM, I forget what it stands for. And there's a third, the name of which escapes me right now. And these are things we could consider. My view of it is we would probably opt to try to put something into the function repository first and see how well it stands up to actual to examples and usage before trying to promote it. But the company may have other ideas. I don't dictate what we actually end up implementing. So that's really all I have to say about
and
that.
of course, matrices will keep coming because we have always ideas. But thanks, Danny. And I mean, honestly, I have a deep interest in asymptotic. So it looks to me like almost like an asymptotic method. I'm sure consider the Adamine method. And so I think that we need to have some kind of better support of those hybrid areas, but we don't have anyone who has got that mindset or even agrees with it. There are the pure numerics people. So there's some kind of a tussle over there, but hopefully we'll get to it. But Brandon is a very experienced user. I respect him deeply, and we have noted your suggestions. So thank you, Brandon. I do appreciate your question. Okay, maybe we can go on to Oliver or Martin. Oliver, you have something to add? Go ahead.
Yeah, so I can. So one question was whether we're considering implementing turbulence models for the fluid flow area. And yes, of course, we are. And in fact, I have worked on this in the past, but I got sidetracked into other things that were also important. So I hope that we can come back to implementing turbulence models. That would still need a bit of time, so it's not going to be it's unlikely that we'll have something, or well, I know for sure that we're not going to have something in the next release like for 15.0, but with a bit of luck, I think we might be able to get something off the ground for 15.1 to give a rough time frame on what we're looking at. So we're definitely interested in this. It's been requested many times, and we're working our way towards it, and hopefully have to offer something in this area soon enough. That being said, there is nothing holding you back to implement your own turbulence models if you would like to do something like that. It's not entirely trivial because these models are extremely nonlinear, so you'll have to use some kind of an iterative approach, and that's exactly the same thing like what we would probably implement or what I've tried to implement in the past. So the underlying technology like NDSolve is capable of solving these type of problems. It's a matter of setting it up properly and being able to call NDSolve in the right iterative procedure to actually solve these highly nonlinear problems. But we'll get there sooner, hopefully sooner than later. Yeah. Okay, that's what I can comment on the turbulence models. Yeah.
Okay, so I think as you can see, we've reached the very end of. Thank you, Oliver. It's really, I think turbulence is a great idea. It's a great idea in physics and a great idea in computing. So let's hope we can get there. And thank you very much for that question. It's a great suggestion. We'll do our best. I promise you I'll support it for sure. And so as you can see, we reached the very last topic, system modelers. So we have a minute more before we close up. If Ankit has something to contribute to the discussion, go ahead, Ankit.
I will just extend what Oliver said. Turbulence models are important, and I think the integration of system modeler, that is lumped models, with the FEM models would be a really interesting use case for the engineering domain. So I'm looking forward to it.
Great. Thank you. So I should just say that Navier-Stokes is a unifying theme, and so Martin spoke about Navier-Stokes, and turbulence is Navier-Stokes, and then Ankit mentioned some of it in his talk, and just yesterday finished approving the final video for a course on PDs, which will be released later in the fall by Aram Manasalian. And guess what? The final lecture, the final video in that series is, again, the Navier-Stokes equations from a symbolic point of view. Simple things, but very important. So I think that PDs are important, computation is important, but Navier-Stokes and turbulence, I think, rule in my mind. So on that note, I think we've answered all the questions, but unless someone is saying more, we'll close over here with a thank you to all of you for giving us so much encouragement by coming here, to Rob's and Jamie and all the WolframU team for being there. Sergio, I can see, has also joined us. So
Devendra, I want to interrupt. There is a late breaking question if you have a chance.
Okay, sure, of course. Right. Okay, let me see. Okay, so right. So from YouTube, any plan for optical simulation that reoptics, and I think that's something that people have. We've had something from early on. I remember a long time ago we had Optica. I'll pass it along to right people unless Oliver or Ankit wants to answer that. I think it's just something for encouraging.
I can quickly comment on the PDE aspect of it. That's not ray optics. I understand that, of course. I think for ray optics, I think Optica is still the thing to use.
Yes.
That we have. From the PDE version, I mean, we have material in the electromagnetics stuff. What we lack still is a prepackaged full full Maxwell equation setup. I mean, you can do this again. You can do this now already, but it's not prepackaged yet. But that's PDE type of an approach for optics. It's not quite ray optics. So maybe.
Yes. So Optica still, as Christopher French just pointed out, Optica still around. Do use the developers he's put his heart into it over the last several decades. So I think that's the way to go. Okay, just so that people can leave. Thank you very much, everyone, for being with us today, and we do appreciate all the effort from everyone's support. And with those words, I'll close today's session. It's been great having you here.